Last time, we talked about the real line, and how to take this one-dimensional number system and turn it into a two-dimensional number system by adding a second axis, giving us R2. And in this two-dimensional universe of the plane, we talked about points, and we talked about vectors, and the things that we could do with them. Now, is it possible to take this two-dimensional universe of R2 and to somehow convert it into a three-dimensional universe, R3? How would we do that? Well, it seems as though we would need to add another axis that passes through the other two, but is perpendicular to both of those. Give it a moment's of thought. Pretty much the only way you're going to be able to do that is to make that third axis stick straight out of the plane. That's going to be a little bit hard to draw in this picture. So let's go and try to take our plane R2 and lay it flat so we can get an idea of what's going on here. So I'm going to take my plane R2, I'm going to sort of visualize it as this kind of flat sheet of paper, and I'm going to lay it down flat, like this. So I have this flat piece of paper here. In this flat plane, I've got the x-axis, who's running east and west, and I've got the y-axis, who's running north and south. And now I can see where I would want to stick this third axis. It should stick straight up out of the plane and then down below the plane. And it seems reasonable that this third axis should be called the z-axis. If we have our three axes, and we have some sort of unit of measure on all of them, so that I can measure distance, both east, west, north, south, and up and down, then we're going to call this universe R3, what's known as Euclidean three-dimensional space, or Cartesian three-dimensional space, or simply 3 space. This is going to be our mathematical model of a three-dimensional universe. You can imagine that this is a model of the world around you. Inside this space, this three-dimensional space, you'll have objects like this, points. Now this picture is a little bit hard to figure out what's going on here, because I'm trying to convey the idea that this point is somehow resting slightly above the xy plane. And if I were to draw this point right here, again, it's kind of hard to get a sense of where this is unless I sort of, again, give you some help and would suggest that this point is below the xy plane. And if I were to draw this point right here, well, this time I actually mean that this point is right there on that z-axis. So we have a three-dimensional space, and we have points inside of it. And every single one of these points we can go and give an addressing scheme for. For example, if we were to take this red point right here, how would we describe how to get to this point starting from the origin? Well, when it was just the real line, we described how far a point was either east or west. When we were in the flat two-dimensional plane, we described how far a point was east-west, followed by how far it was north-south. So in a three-dimensional world, well, it seems as though we should start off by describing how far east or west it is, in this case, 2 points east, then how far north and south it is, in this case, 1 unit north, and then finally, how far above or below the plane this point is. In this case, it's 1, 2, 3, 4 units up. So 2 units east, 1 unit north, and then 4 units up above the plane. If you'd like to think of it, you can think of it as an altitude, the xy plane being sea level, and this point being 4 units above sea level. And so the address that we're going to write for this point will be 2, 1, 4. And so these are going to become the coordinates of this particular point. If we instead focus on this purple point right here, starting from the origin, to get to the purple point, we would go 2 units to the east, and then in this case, 1 unit south, followed by 1 unit below the xy plane. So that would be 2 units in the direction parallel to the x-axis, -1 units in the direction parallel to the y-axis, and then we would drop down -1 unit below the xy plane. And so we would write the address of this point as being 2, -1, -1. And finally, if we looked at this green point, well, to get to this green point, I don't travel east-west or north-south. I just go straight up 2 notches. And so his coordinates would be 0, 0, 2. So just as in R2, every point in three-dimensional space is represented by coordinates, an ordered triple of real numbers who describes the address of that particular point. Let's take one more look at the coordinate system we just came up with. So here's a picture of the xy plane again. We're going to have the x-axis running this way, east and west through it. We'll have the y-axis running north and south through it. And then we'll have the z-axis sticking up out of the plane and then down below the plane. So if we were to have a point, say this particular point in three-dimensional space, we could sort of see its shadow in the xy plane right here. This shadow is sometimes called the projection of this point in the xy plane. Now the coordinates of this point are going to be the distance that this point is displaced starting from the origin along a direction parallel to the x-axis, say x units, followed by a right angle displacement north and south parallel to the y-axis of y units, followed by another right-angled turn straight up out of the plane, z units parallel to the z-axis. And if we get to this point by traveling x units east, y units north, and z units up, then the coordinates of this point are going to be x, y, z. In R2, these were called rectangular coordinates, and in R3, we're going to call them the exact same thing. And again, the intuitive picture is that these coordinates actually describe the sides of a rectangle for which the origin and the point xyz are opposite corners. However, just like in R2, this isn't the only coordinate system that you could use. Remember that in R2, if we wanted to describe a point in the Euclidean plane, so just the x, y space right here, we could use east-west and north-south descriptions, rectangular coordinates, but we could also describe a point in the xy plane by measuring its distance from the origin, a radial distance we called r, and the angle that this radius made with the positive x-axis, an angle we called theta. And so r and theta were what we were calling polar coordinates in R2. Well, we could use those same points right here, and instead of using x, y, we could also write the address of this point as being r theta. That describes the location of the projection, the shadow, and then we'll follow up with z units up above the xy plane. This is called cylindrical coordinates. It's essentially polar coordinates r theta giving the description of the location of the shadow, the projection, followed by the z-coordinate giving the height of the point above the x-axis. If you recall from last time too, we had equations that allowed us to go back and forth between polar coordinates r theta and rectangular coordinates x, y. Those equations were x equals r cosine theta, y equals r sine theta, r equals the square root of x squared plus y squared, and the tangent of theta equals y over x. If we add one final equation, the trivial statement z equals z, since the z-coordinate is the same in either one of the polar, in either rectangular or cylindrical coordinates, then these 5 equations are called conversion formulas between cylindrical and polar coordinates. And the best way to understand them is to try putting them into practice. Let's take a look at this example. Convert the points -2, 0, 2, √3, 1, -2, and 1, 1, 1 from rectangular coordinates into cylindrical coordinates. So let's start off with this first guy right here. And I'm going to draw kind of a cheesy picture just so I have some intuition as to what's happening. So here's the x and y axes laying flat in the plane, and here's the z-axis sticking up out of it. And so this point would be 2 units to the left of the origin, 0 units above or below, so there would be its projection, and then it would be 2 units up. So its projection would lie at the point minus 2, 0 in the xy plane, and then it would be 2 units above that. So there's two different ways that we could work out what his his cylindrical coordinates are. One of them is to simply use common sense in the definitions. Since the projection is 2 units away from the origin, and it makes a 180-degree angle with the positive x-axis, we would know that r would be 2 and theta would be 180 degrees, or pi. Since the z component of cylindrical coordinates is the height, we would know that z is equal to 2, and so the cylindrical coordinates would be r theta z equals 2 pi 2. A slightly different attack is to simply use those formulas. We know that x is equal to minus 2 and y is equal to 0. So r will be the square root of x squared, which is 4, plus y squared, which is 0, and the square root of 4 is 2. We also know that the tangent of theta is equal to the y value over the x value, in this case 0 over negative 2, or 0. So we have an angle whose tangent is theta. If we compute the arctangent of that, the arctangent of 0 is 0. Well, that's clearly the wrong angle right here. It's an angle in quadrant 1 or 4, and our point is clearly over there near quadrants 2 and 3, and so we're going to have to fix that by adding 180 degrees to it. And so we get 180 degrees, or pi radians. And so once again, we recover this polar description. Next, let's take a look at this point right here. So this point is going to be root 3 units along the x direction, so that's about 1.7 units, 1 unit in the y direction, and then it will be 2 units below the plane. So if we were to find its projection in the plane, this point right here, that would be the point root 3, 1 in the xy plane, and then it drops down 2. So again, let's attack the problem of finding his cylindrical coordinates two ways. The first is by the definition, and the second is by the conversion formulas. So the r and theta values are simply the polar coordinate descriptions of the point of the projection in the plane. Since this is a right triangle in the plane, the Pythagorean Theorem tells us, well, this is root 3, this is 1. The Pythagorean Theorem tells us that the missing side is a 2, and so the radial distance is a 2. Also, a 1 root 3 triangle is a 30, 60, 90 triangle, and so this angle has to be 30 degrees. So theta will be pi over 6. Since the z-coordinate is the same in either one of these systems, and in this case it's 2 units below the x-axis, we know that z is equal to negative 2, and so the polar coordinate description will be r theta z equals 2 pi over 6 negative 2. Alternatively, we could use the conversion formulas. We know that x is equal to root 3 and y is equal to 1. So the r value will be the square root of x squared, which is 3, plus y squared, which is 1. That gets me the square root of 4, or 2. We would also know that the tangent of theta would be equal to the y value 1 over the x value root 3. If we compute the inverse tangent, the arctangent of 1 over root 3, well, that's one of our basic trig identities. The inverse tangent of 1 over root 3 is 30 degrees. Based on our picture, our projection is in quadrant 2. The arctangent is an angle in quadrant 2. This is the right guy. So we've recovered r and theta, and the z value is still negative 2. And so that would be the cylindrical coordinate description of the point root 3, 1, minus 2. Finally, let's take a look at 1, 1, 1. So this would be a point 1 unit over, 1 unit north, and 1 unit above the plane, the xy plane. So its projection in the xy plane would be the point 1, 1, and then it would be 1 unit higher than that. So based on this picture, the distance the projection is from the origin, well, this is a right triangle with sides of 1 and 1. That means the hypotenuse is a 2, so the r value would be root 2. Also, a 1, 1, root 2 triangle is a 45, 45, 90 triangle, and so this would be a 45-degree reference angle. So we'd have theta is equal to pi over 4. Since the z value is the height above the x-axis, z would be 1, and so we have a polar coordinate description. Our theta z would be root 2 pi over 4 and 1. I'll leave it as an exercise to you to try it using the conversion formulas. Now, it turns out that while there was only one way to coordinatize points on the real line and two ways to coordinatize points in the two-dimensional R2, there's actually three ways to coordinatize points in the three-dimensional world of R3. This third description is kind of a perfect generalization of the idea of polar coordinates to a three-dimensional universe. And so I'd like to describe it for you right now. So imagine we have a point floating around in R3. This third coordinate description starts by measuring the distance between that point and the origin. So this distance right here is going to be called rho. Next, we're going to take the point rho, the point in question, the origin, and the projection in the xy plane. And we're going to consider this right triangle right here, and we're going to measure two angles based off of this triangle. The first angle we're going to measure is the angle it makes, the angle the base makes with the positive x-axis in the xy plane, and we'll call this angle theta. So this angle theta is essentially a longitude. The other angle we're going to measure is we're going to measure the angle the hypotenuse makes with the positive z-axis. So we're going to measure down from the positive z-axis to this, and we're going to call this third angle, or the second angle, phi. So this angle phi is essentially a latitude. If we put these three things together, rho theta phi is called this point's spherical coordinates. You can actually see that the spherical coordinates are related to the other coordinate systems. If, for example, we were to go and draw the rectangular coordinates overlaid on top, so we would have x running along the x-axis, y running perpendicular to the x-axis, and then z running perpendicular up out of the plane, we can also see the cylindrical coordinates running around in here in terms of the angle theta and the distance r along the base of this triangle right here. This means we have lots of equations that we can write down that would allow us to convert back and forth between these three coordinate systems. To write down what these equations are, let me call your attention to this particular triangle. Since this triangle right here is a right triangle, we can apply the Pythagorean Theorem and Trigonometric Identities to it. For example, the Pythagorean Theorem would say that rho squared is equal to r squared plus z squared. Also, since the z-axis is parallel to this z component, a theorem from geometry says that the angle phi made from the hypotenuse and the z-axis is the same as the angle from the z component to the hypotenuse. This is what I believe is known as the alternate interior angles theorem from geometry. So now that we have an angle right here, we can write down a few more trigonometric identities. For example, if we were to take the ratio of the adjacent side to the hypotenuse, z over rho, that would be the cosine of the angle phi. And if we were to take the ratio of the opposite side, r over the hypotenuse, rho, we would have the sine of the angle phi. Finally, if we take the ratio of the opposite side r to the hypotenuse, to the adjacent side z, we would have the tangent of phi. So, if we rearrange some of these equations as follows, we would have rho is equal to the square root of r squared plus z squared. The tangent of phi is r over z. R is rho sine theta, and z is rho cosine. Rho is r sine phi, and z is rho cosine phi. If we add a third equation to this mix, namely the trivial equation that theta is equal to theta, then what we have are 5 equations that allow us to convert between the green cylindrical coordinates r, z, theta into the orange spherical coordinates rho, theta, phi, and back again. So these are cylindrical to polar conversion formulas. If we further remember that r squared is itself x squared plus y squared from the polar to rectangular conversions, we can also write this first equation as rho equals the square root of x squared plus y squared plus z squared. Similarly, the second equation can be rewritten as tangent of phi equals the square root of x squared plus y squared over z. Finally, we also know the conversion formula for theta, namely tangent theta equals y over x. So these 3 equations allow us to convert from the purple rectangular coordinates into the orange cylindrical or spherical coordinates. Finally, from our rectangular polar conversion formulas, we know that x is equal to r cosine theta and y is equal to r sine theta. But remember, r is equal to rho sine phi. So if we take this and substitute it in for these 2 values of r, we obtain x is equal to rho sine phi cosine theta and y is rho sine phi sine theta. If we just copy this equation down one more time, we get z is equal to rho cosine phi. And so now we have the 3 equations that allow us to convert from the orange cylindrical coordinates back into the purple rectangular coordinates. And so there we have a complete list of conversions from the new spherical coordinates into the 2 other coordinate systems, rectangular and cylindrical, that we're more familiar with. Again, the best way to practice this is on examples. So let's go and revisit the 3 points we looked at before. Convert the points -2, 0, 2, root 3, 1, minus 2, and 1, 1, 1 into not cylindrical coordinates, but spherical coordinates. So let's start this process over again with the point -2, 0, 2. So remember that was a point who went -2 units in the x direction, nothing in the y direction, and then 2 units above the plane. So we'll do this 2 different ways. One by using the definition of spherical coordinates, and then by using the conversion formulas. So by the definition, the first thing we'd measure is the distance from this point to the origin, rho. Well, in this case, this is just right off of the x-axis. Since this is a right triangle, we could use the Pythagorean Theorem to find out that rho is equal to the square root of 2 squared plus 2 squared. So rho is equal to the square root of 8, or 2 root 2. The next thing we need to do is to take this triangle right here, the triangle that sticks out of the xy axis, and to measure the angle it makes with the positive x-axis. Well, that angle, since it's pointing on the negative x side, is clearly 180 degrees. So that's the angle theta, the longitude, which we always write as radians pi. Finally, the last thing we have to do is we have to measure the angle between this hypotenuse and the positive z-axis. Well, since this whole picture takes place in the plane spanned by the x and the z-axes, and this is a isosceles right triangle, this is a 45-degree angle, which means that this is a 45-degree angle. And so phi has to be 45 degrees, or pi over 4. And therefore, the spherical coordinates would be rho theta phi equals 2 root 2 pi over 4. Alternatively, we could use the different conversion formulas. For example, the conversion formula for rho said that rho is equal to the square root of x squared plus y squared plus z squared. In this case, -2 squared is 4, 0 squared is 0, and 2 squared is 4. And so we get the square root of 8, or 2 root 2. which checks with the previous result. We can solve for theta by the equation tangent of theta is equal to y over x. So the tangent of theta is equal to 0 over -2, or 0. So that means that theta is equal to the arctangent of 0, 0 degrees, up to a multiple of 180 degrees. And since we're not in quadrant 1 or 4, we're going to need to add 180 degrees to that. And so we'll get 180 degrees, or pi, which checks out with the next example, or checks out with our previous work. Finally, the tangent of phi is equal to the square root of x squared plus y squared over z. So in this case, the square root of x squared plus y squared, that's the square root of 4 plus 0 over 2. So that's going to get me 2 over 2, or 1. So that means that theta should be, sorry, not theta, this is the other variable, phi should be the arctangent of 1, which is 45 degrees. And since this is, based on the picture, an acute angle, that seems like that's the right choice. And so again, we recover pi over 4. And so here are the spherical coordinates of the point -2, 0, 2. They're 2 root 2 pi, pi over 4. Next, let's take a look at this point right here. So this is the point that goes root 3 units in the x direction, about 1.7, 1 unit in the y direction, and then from there drops below the x-y plane to go 2 units down below. So let's put this thing in its spherical coordinates. Now there's 2 ways we could do this. We can do the definition or the conversion formulas. Let's start off by using the conversion formulas. So we're going to first measure the distance from the origin to this point down here. So let's take a look at what this triangle is right here. This is a triangle who lives below the x-axis. It's a right triangle. It has a side of length -2, the side that goes down here. The other side of this triangle who goes below the x-axis is actually the hypotenuse of this right triangle who lives in the xy plane. Since this triangle has sides of root 3 and 1, the missing side by the Pythagorean Theorem is 2. So that means, if I draw a copy of this triangle over again, the triangle that's living below the x-axis has a length of 2 above it and a length of -2 below it. And so the hypotenuse is going to be the square root of 2 squared plus 2 squared. That's 2 root 2, based on the work we did last time. So this distance rho is going to be 2 root 2. Whew. That was kind of crazy. The next thing we got to do is we have to figure out the angle theta made by this purple triangle, the triangle that connects the point, the origin, and the projection, with the positive x-axis. Well, that's nothing more than the angle formed by this right triangle in the plane. Since this is a 1, root 3, 2 triangle, that tells me this is a 30, 60, 90 triangle, and so this angle right here should be 30 degrees. So now we know that theta is 30 degrees, or pi over 6. Finally, phi is the angle made by the hypotenuse of the purple triangle, the triangle that's underneath the xy plane, and the positive z-axis. So we're measuring this angle down here, a latitudinal angle. Now, our work over here, this is what the triangle below the xy plane looks like. It was on isosceles right triangle, which meant that this is 45 degrees as a reference angle. So to get to this, starting from the positive z-axis, we would have to go down 90 degrees to get to the xy plane, and then an additional 45 degrees to get down below it. So phi would have to be 90 degrees plus 45 degrees. That's 135 degrees, or 3 pi over 4. Therefore, the spherical coordinates will be rho, theta, phi equals 2 root 2, pi over 6, and 3 pi over 4. Alternatively, we could go and use the conversion formulas. The first conversion formula rho would say that we're looking for the square root of x squared plus y squared plus z squared. So in this case, that would be the square root of x is root 3, so root 3 squared is 3, plus 1 squared, plus 2 squared. So that's the square root of 8, or 2 root 2, which checks with our previous work. We would know that the tangent of theta would satisfy y over x. The y value is 1, the x value is root 3. And so the tangent of theta equals 1 over root 3 means that theta has to be a 30-degree angle, as long as it's in quadrant 1 or 4. And in this case, that angle was in quadrant 1. Finally, we would know that the tangent of the angle phi would be the square root of x squared plus y squared over z. So that would be the square root of 3 plus 1 over 4. So that would be not over 4. Z is negative 2. So that's going to get me the square root of 4, which is 2 over negative 2, or negative 1. That means that phi is going to be the arctangent of negative 1, which is negative 45 degrees. However, based on the picture, we're clearly looking for an obtuse angle, something that's in quadrant 2. So we're going to have to add 180 degrees to this to correct for that. And that'll put me at 135 degrees, or 3 pi over 4. And so once again, we recover the same polar coordinate description. Lastly, let's take a look at this point right here. The point who's 1 unit over, 1 unit north, and then 1 unit above the xy plane. In this case, I'm just going to go through and use the conversion formulas to figure out what this point is right here. So working our way with the conversion formulas, the first value, rho, is going to be the square root of x squared plus y squared plus z squared. So in this case, we're going to have the square root of 1 plus 1 plus 1, or the square root of 3. Next, the angle theta, the angle made by the base of this triangle floating upwards and the positive x-axis, can be found by solving tangent theta equals y over x. So 1 over 1, or 1. That tells me that theta is equal to the arctangent of 1, or 45 degrees, as long as we're in the right quadrant. And sort of based on my crude sketch here, this clearly looks like this is in quadrant 1. And so we'll take that one, pi over 4. Finally, the angle phi, the angle measured from the positive z-axis to the hypotenuse of the triangle who's standing above the xy plane, can be found by solving the equation tangent phi is equal to the square root of x squared plus y squared over z. So that's going to be the square root of 1 plus 1 over z, which is 1, or the square root of 2 over 1. So phi is going to be the arctangent of the square root of 2. Unfortunately, that's not one of the basic triangles with which I'm familiar. If I was going to attempt to draw a picture for solving that, we would have an angle phi here, and the tangent is the opposite over the adjacent, which means that the missing side by the Pythagorean Theorem would be a root 3. And the 1 root 2 root 3 triangle isn't one I happen to know. And so this is about the best I can do with this particular guy. It's an exact value, even if it's not particularly helpful. And so we find that the spherical coordinates, rho, theta, phi, are going to be root 3, pi over 4, and the arctangent of the square root of 2. Of course, points weren't the only thing that were in R2, and they're not the only thing that happens to be in R3 as well. We can also talk about vectors. So all a vector is just like in R2, it's an equivalence class of directed line segments in R3. So any collection of line segments in R3 that point in the same direction and have the same length would all describe a common vector. Imagine for a moment we were to isolate one of these vectors and locate its tail and its tip. If we traverse from the tail to the tip by traveling parallel to the x-axis a units, then parallel to the y-axis b units, and then parallel to the z-axis c units, then we will call this vector the vector bracket A, B, C, or in component form, or in column form, sorry, A, B, C. Thus, every single one of these purple line segments would represent the exact same vector right here. How many of the concepts from R2 would carry over to vectors in three-dimensional space? Well, it turns out all of them will. For example, if you were given a vector v, like this vector right here, then scaling would make complete sense. To double the vector v, we would simply take the same vector but make it twice as long. Whereas to halve the vector v, we would simply take the same line segment, but we would make the new tip at the midpoint. Or to negate the vector v, we would simply replace the tail and the tip, and we would have an opposite. So vector scaling makes complete geometric sense in the plane, and although the picture is a little bit more complicated to work on, the formula stays the same. If we would have a vector A, B, C, and we were to scale it by the scalar lambda, then we would simply scale each one of the components, lambda A, lambda B, lambda C. So vector scaling is still a valid operation in R3. Well, what about vector addition? Well, the basic construct that we had done last time would still make sense. If we were given a second vector w, we could translate that vector so that the tail of the vector w starts at the tip of the vector v. This would give us a tail point at the tail of v and a tip point at the tip of the translated vector w, and so we could connect the line segment through these 2 points, and we would have the vector v plus w. So the geometric idea of adding 2 vectors makes sense in three-dimensional space, although it's a little bit harder to draw the picture. It also works on the component side. If the first vector v had components a, b, c, and the second vector w had components s, t, u, then when we add these 2 vectors up, we would simply add along the components a plus s, b plus t, and c plus u. So just like in R2, vector addition is done component-wise. What about the concept of magnitude of a vector? How long a vector is? Well, imagine we were to go and take this vector, v, and translate it back down to the origin. Well then, the length of this vector would be nothing more than the value rho in the polar description of the point who is at the tip of the vector v. Now, if the vector v has components a, b, c, then the point at the tip right here must be the point a, b, c, since we've started its tail at the origin 0, 0, 0. So using our polar coordinate conversion formula, we would know that the rho value in its cylindrical coordinates would have to be rho equals the square root of the x component plus the y component plus the z component. But this value right here is nothing more than the length of the vector v we're looking for. So there is some utility in all this trig out there. Let's summarize this once more. If v is the vector a, b, c, then the magnitude of v, its Euclidean length, is going to be the square root of a squared plus b squared plus c squared. This kind of has a nice similarity with what we saw in R2. Remember, in R2, if you have the vector AB, then its magnitude was given by the square root of a squared plus b squared. Heck, if you even go back 1 dimension and you just had a real number, a, then the magnitude of the real number a would be what we would call absolute value in the real case. And if we were to follow this formula down, we would get the square root of a squared And if you think about that, the square root of a squared is exactly what the absolute value of a is. So what we've been doing is we've been coming up with a way that generalizes the addition, the multiplication, and the absolute value from real numbers into larger and larger spaces. It's kind of neat when you think about it from that point of view. Finally, the last idea we talked about from vectors in the last section was the notion of the standard basis. Now, if you remember what the standard basis was, it was two vectors in R2. The first was a vector who pointed 1 unit in the direction parallel to the positive x-axis. This vector right here was called I. And in R3, I has the components 1, 0, 0. 1 unit parallel and pointing in the direction of positive x. There was a second standard basis vector in R2. 1 unit long and pointing in the direction of positive y. This vector was called j, and in R3 its components would be 0, 1, 0. Well, now we have a third dimension to work with, and so we would have a third standard basis vector, a vector k, who points 1 unit up, and so its components would be 0, 0, 1. So taken together, the vectors I, j, and k are called the standard basis. And just like last time, if you had a vector a, b, c, well, we could split this vector apart as a, 0, 0 plus 0b, 0 plus 0, 0, c by using the rule for vector addition. Then by using the rule for vector scaling, this first thing is a times the vector 1, 0, 0. The second vector is b times the vector 0, 1, 0. And this third vector is c times the vector 0, 0, 1. But the vector 1, 0, 0 is is the vector I. The vector 0, 1, 0 is the vector j. And the vector 0, 0, 1 is c. The vector 0, 0, 1 is k. And so what we found out is that if we were to go and take our vector v, who had components a, b, c, it could be expressed as ai plus bj plus ck. So just like last time, every vector can be expressed in terms of a standard basis, and the components of the vector are just the scalars in front of the standard basis vectors. So let's take a look at an example or two, just to make sure we understand these. Let v be the vector from the point 1, 1, 3 to the point 2, 0, 6, and w be the vector 3i plus 2j minus k. Compute the vector z, whose 3v minus 2w. Just like last time, in R2, the easiest way to do vector calculations is to convert all of the vectors into a common form. I'm a big fan of the column component form, so let's go and do that. W is actually kind of easy to convert over. W is written in the standard basis form, but the coefficients in the standard basis are going to be nothing more than his vector components. So this is going to be a vector who goes 3 units in the x direction, 2 units in the y direction, and -1 units in the z direction. The vector v is going to take a little bit more effort right here. But if we think about it, the vector v is going to go from the point 1, 1, 3 to the point 2, 0, 6. So let's just think about this kind of quickly here. To get from the point 1, 1, 3 to the point 2, 0, 6, that means that the x-coordinate had to go up by 1. The y-coordinate had to go down by -1. And the z-coordinate had to go up by 3. So this should be the vector 1, -1, 3. Alternatively, you might remember from the last section that we compute in R2 the vector from tip to tail by taking the tail and subtracting the tip. And you'll notice that 2 minus 1 is 1, 0 minus 1 is -1, and 6 minus 3 is 3. What worked in R2 is going to work over here in R3 as well. This is the good utility of these vectors. So now that we have these two pieces, we can go and compute z. Z is going to be 3 times the vector v 1 minus 1, 3, minus 2 times the vector w, which is 3, 2, minus 1. So the first thing I'm going to do is do the two vector scalings. So if I scale the first vector by a 3, I'm going to get 3 minus 3, 9. If I scale the second vector by a negative 2, I'm going to get negative 6, negative 4, positive 2. And then I'll add these two vectors up. So I add across the rows. 3 plus negative 6 is negative 3. Negative 3 plus negative 4 is negative 7. And 9 plus 2 is 11. So that tells me that the vector z is minus 3, minus 7, 11. Or in its row component form, minus 3, minus 7, 11. Or if you'd prefer the standard basis, minus 3i, minus 7j, plus 11k. And so there's the vector z. Find a unit vector that points in the opposite direction of the vector 2i minus 6j plus 3k. Well, let's call this vector v right now. And I'm just going to draw sort of a cheesy representation of what's going on here. Here's the vector v. It goes 2 units over, then 6 units down, and then 3 units above the xy plane. So yeah, there it is. If I were to write this vector in its column component form, then it would be 2 minus 6, 3. So we're looking for a vector who's 1 unit long. That's what a unit vector is, but who points in the same direction. You might remember last time that was the process we called normalizing. To get a unit vector who points in the same direction as v, we would take the vector v and we would multiply by 1 over its magnitude. We would divide by its length. So let's, compute its length and do the division right here. So the length of v is going to be the square root of the sum of the squares of its components. So 2 squared plus 6 squared plus 3 squared. So 4 plus 36 plus 9. Well, that's the same thing as the square root of 40 plus 9, or 49. And the square root of 49 is 7. So this vector is exactly 7 units long. So if we take the vector 2 minus 6, 3, and multiply it by 1/7, we're going to get the vector 2/7 minus 6/7, 3/7, as a vector who's 1 unit long, who points in the exact same direction as the vector 2i minus 6j plus 3k. But wait a second. The problem asked for a vector who points in the opposite direction, not the same direction. Try to pull a fast one on me right here. But that's no problem. If this vector points in the exact same direction, the negative u, the vector negative 2/7, positive 6/7, minus 3/7, has the same length as the vector u, so it's length 1, but it points in the opposite direction. And so this would be the vector we would want to work with.